Welcome to our Quantum Deep Dive. Today we're taking a plunge into one of the most fundamental, yet, well, endlessly mysterious forces in our universe. Gravity. It's this invisible architect shaping everything, isn't it? From, the simple fall of an apple to the majestic dance of galaxies across the cosmos. To guide us through this incredible journey, we're drawing insights from a really brilliant essay titled Gravitation Theory, Understanding the Foundations of Gravity by Yorgo Schneeppert. Our mission today is to sort of unpack humanity's evolving understanding of gravity. We'll go from ancient philosophical musings all the way to cutting-edge quantum physics and explore the profound questions that are still puzzling scientists. Okay, let's unpack this. How do we even begin to understand something so fundamental, yet, so elusive? I mean, before the equations, before telescopes even, how did humans try to make sense of why things fall? The ancient Greeks, for instance, had a fascinating take, Aristotle, right? His ideas held sway for centuries. He believed that gravity wasn't some universal force pulling things together, but, that bodies simply sought their natural place.
Heavy things, like rocks, filled Earth because Earth was their natural home. It's almost charmingly poetic, isn't it? A rock just wanting to go home. It really shows how fundamental that question, why do things fall, has been for literally millennia, way before anyone dreamed of equations.
It is quite remarkable. Even without the math, these early ideas tried to establish some kind of order, a purpose to movement. Okay, so it was incorrect by our modern understanding, but that pursuit of order was crucial. It paved the way for questioning. And these concepts, they stuck around for centuries. But as we move into the medieval period, we start seeing these glimpses of more empirical thinking. You had thinkers like Jean Bourdin introducing the idea of impetus, a kind of internal force keeping a thrown object moving. That was a really crucial precursor to our modern concept of inertia. And Nicole Resme even theorized about uniform acceleration for falling bodies, laying some of the earliest groundwork for a mathematical approach. The real insight here, I think, is how these early, sometimes incorrect ideas were actually vital. They established the need for an underlying order and, crucially, began planting the seeds for a mathematical description of movement.
Then came a giant who truly changed everything. Isaac Newton, right? With his groundbreaking work, Principia Mathematica, published in 1687. Newton didn't just explain falling apples. He proposed a truly universal law of gravitation. He basically said every object with mass attracts every other object with mass. That's a huge claim. How did he manage to capture such a grand overarching concept in a way that was both, simple and incredibly powerful?
He distilled it into that iconic equation, F = m·i·m·a·r·o. The genius is in its elegant simplicity, really. It just states that the force of gravity between any two objects is directly proportional to the product of their masses, and, this is key, inversely proportional to the square of the distance separating them. This single formula, it unified the heavens and the earth under one law. Suddenly, you can make precise predictions for everything from planetary orbits to the tides. It became the absolute bedrock of classical physics, enabling incredible advancements in celestial mechanics, navigation, everything really.
Okay, so Newton's work was monumental, clearly explained so much. But it still left some anomalies, didn't it? I'm thinking of something like Mercury's orbit. Did scientists back then just think they needed, more refined calculations, or were there whispers that maybe something much deeper was going on?
Indeed. Yeah, while Newton's theory was remarkably accurate for most things, it did struggle with a few subtle discrepancies. The most famous was that slight, inexplicable precession of Mercury's perihelion, the point in its orbit closest to the sun. Newtonian physics just couldn't fully account for it. And beyond that, the whole concept of action at a distance, gravity seeming to instantaneously pull objects across vast distances, that started to feel inconsistent later on, especially once the finite speed of light was established. These weren't exactly failures, but they were significant cracks in the edifice, definitely hinting that something was missing.
And just when we thought we had gravity largely figured out, boom.
Right.
Albert Einstein comes along and completely rewrites the rulebook with his General Theory of Relativity, or RT, published in 1915. Einstein proposed something truly radical. Gravity isn't a force at all, but it's a manifestation of the curvature of a four-dimensional space-time caused by mass and energy. I mean, that's a mind-bending idea. Can you give us an analogy to help us wrap our heads around that?
Absolutely. It's a classic one, but it works. Imagine you place a bowling ball on a stretched rubber sheet. It creates a dip, right?
Right.
Now, if you roll some marbles nearby, they aren't really pulled by the bowling ball in the traditional sense. Instead, they just follow the curve. They roll into the dip created by its weight. That's essentially how Einstein envisioned it. Mass and energy tell space-time how to curve, and space-time's curvature then tells matter how to move.
Okay, so how did Einstein capture this revolutionary idea?
Mass telling space-time how to curve, space-time telling matter how to move. How did he put that into a single mathematical framework?
He did it with what we now call the Einstein field equations. Now, without getting totally lost in all the Greek letters and tensors, the beautiful core idea is this. One side of the equation describes the geometry of space-time, like how warped and bumpy it is. The other side describes all the matter and energy present in that space. So it's essentially this cosmic dialogue. Matter and energy dictate the bending of space-time, and space-time's curvature dictates how matter and energy move.
That's such a crucial point because an elegant theory is one thing, but proving it in the real world, that's something else entirely.
Yeah.
How did scientists actually test Einstein's radical vision? What were the undeniable proofs that it wasn't just some clever mathematical trick?
Oh, the confirmations have been astounding, really. First off, RT perfectly explained that long-standing mystery of Mercury's perihelion precession. Nailed it.
Wow, okay.
Then, famously, in 1919, observations during a solar eclipse confirmed Einstein's prediction that the sun's gravity would actually deflect starlight, bending it as it passed by.
Bending light itself.
Exactly. And then, in a truly spectacular validation just a few years ago, in 2015, the direct detection of gravitational waves by LIGO.
Ah, yes, the ripples in space-time.
Precisely. Ripples caused by colossal cosmic events like black holes colliding, that detection really cemented RT's validity beyond pretty much any doubt.
And it's not just elegant math. These confirmations proved Einstein wasn't just describing gravity, he was revealing this hidden layer of reality itself. And that new reality, that warped space-time, it opened the door to understanding some of the universe's most mind-bending phenomena, like black holes. So let's dive a bit deeper into that fabric of reality, the four-dimensional space-time. Einstein showed space and time aren't separate, rigid things, but are intertwined, forming this flexible dynamic continuum. And mathematically, this metric that describes the distances and intervals in this curved space-time. So bodies moving under what we perceive as gravity are actually just following geodesics, basically the shortest paths available in this curved cosmic fabric.
Indeed. What's truly profound here is that gravity, in this view, it stops being an external force. It's just an inherent geometric property of the universe itself, and the Einstein field equations capture this relationship perfectly. Solving these equations has led to some incredible insights and predictions. For instance, the Schwarzschild metric describes space-time around non-rotating spherical masses. That's crucial for understanding stars and, of course, simple black holes.
Okay.
Then you have the Kerr metric for rotating black holes, which is more complex. And the Friedmann-Lemaitre-Robertson-Walker metric, the FLRW metric, that actually describes the large-scale structure of our expanding universe.
And these equations don't just describe what we can see. They predict some truly wild things, like black holes, born from the collapse of massive stars when gravity just overwhelms everything else. They have that event horizon, right? The point of no return. And at the core, a singularity, this point of supposedly infinite density and curvature. And they come in different sizes, too.
Yeah.
Stellar ones from stars, supermassive ones in galaxy centers.
But the profound mystery, of course, is what truly happens at those singularities. Classical physics, general relativity. It just completely breaks down there. Infinite density, infinite curvature. What does that even mean? The real insight here, I think, is that singularities aren't just cosmic curiosities. They're essentially a giant cosmic error message from the universe.
An error message.
Yeah. They signal a fundamental breakdown in general relativity itself. They force us to confront the fact that our understanding of reality at its most extreme limits is incomplete. They're not just physical points. They're the universe screaming for a quantum theory of gravity.
Okay, so general relativity gives us this incredible picture of the big stuff, planets, galaxies, black holes. But then there's the tiny quantum world where probabilities and uncertainty rule. How do we marry these two titans of physics? That's the central challenge, isn't it? General relativity sees space-time as continuous, smooth, predictable. Quantum theory describes a discrete, probabilistic, often, well, bizarre reality. They seem fundamentally incompatible.
Exactly, and one crucial step towards trying to bridge that gap has been something called quantum field theory in curved spacetime. It's a sort of semi-classical approach. Gravity itself is still treated classically using Einstein's equations, but other fields, like the electromagnetic field, are quantized, treated quantum mechanically.
And one of the most profound predictions from that approach is truly mind-bending. Stephen Hawking's discovery of Hawking radiation back in 1974. He showed that black holes aren't entirely black, are they? Quantum effects right near the event horizon cause them to emit this faint thermal radiation and slowly evaporate over unimaginable timescales, but still.
Precisely. And this leads to a fascinating formula. TH equal key KB. Now, without getting lost in the constants, what it essentially tells you is that a black hole's temperature, and therefore its evaporation rate, is directly linked to its surface gravity. Smaller black holes, which have stronger surface gravity near their horizon, would actually evaporate much, much faster than the supermassive ones. And this has huge implications, including this really thorny problem about what happens to information that falls into a black hole, the famous information paradox.
Wait, hang on. If a black hole evaporates and just emits this thermal radiation, what happens to the information? Like if I threw a physics textbook into a black hole, is the information in that book, the actual words, the concepts, just gone forever when it evaporates?
Yeah.
Doesn't that fundamentally break physics? I thought information was supposed to be conserved, never truly lost.
Exactly. That is the absolute crux of the paradox. If the radiation coming out is purely thermal, it carries no information about what fell in. And because the semi-classical approach leads to this paradox, it tells us it's not the final answer either. It forces us to push even further, to build entirely new frameworks, which is where things like string theory and loop quantum gravity come into play.
Right. Since the semi-classical approach isn't quite enough to fully reconcile gravity and quantum mechanics, physicists are building these entirely new frameworks. So tell us about the big players in this quantum gravity game.
Okay, well, one very prominent candidate is string theory. The core idea here is that elementary particles aren't actually point-like objects, but rather tiny, vibrating, one-dimensional strings. And in this theory, gravity isn't something added on. It naturally emerges as a specific vibrational state of a closed string, what we call the graviton.
A vibrating string is gravity.
Wow. Sort of, yeah. Now, string theory often requires extra dimensions, like 10 or 11 space-time dimensions, with the extra ones supposedly curled up incredibly small, way beyond our ability to see directly. Its big advantage is its potential to unify all the fundamental forces, not just gravity, but the challenge, well, the energies and length scales it describes around the Planck length, like 10 to the minus 35 meters, they're just incredibly tiny, making direct experimental tests extremely difficult right now.
That sounds like a whole different universe we'd need to explore. What's the main alternative to string theory then?
The other leading candidate is loop quantum gravity, or LQG. Now, unlike string theory, LQG takes a different approach. It directly tries to quantize spacetime itself. It suggests that spacetime isn't continuous, but is actually discrete at the Planck scale, like it's woven from tiny quantum loops.
So space itself is made of little bits.
That's the idea, and one of its key strengths is that it seems to naturally avoid singularities, like the ones inside black holes. They just don't really appear in the framework, which offers a neat resolution to that error message we talked about. Oh, okay.
LQG is also more directly based on general relativity, but its current challenge is making a clear connection to the other fundamental forces described by the standard model of particle physics. Both string theory and LQG offer these profound, really deep insights, but you have to remember, they're still largely theoretical. Finding that experimental evidence, that's the next huge frontier.
And beyond just uniting the theories we have, the universe itself is throwing us some massive curveballs, isn't it? What exactly are dark matter and dark energy, and why are they such huge challenges for gravity theories?
Yeah, it's humbling, really. Observations tell us that roughly 95% of the universe's total mass energy content is made up of these two mysterious components. Everything we can actually see and interact with directly, stars, planets, us, that's only about 5%.
Just 5%. Just 5%. So, dark matter. It was first postulated way back by Fritz Zwicky in the 1930s. He noticed galaxies were rotating much faster than they should if only the visible matter was providing the gravity. It's also crucial for understanding gravitational lensing, how gravity bends light, and the large-scale structure of the cosmos. We know it interacts gravitationally, but it doesn't seem to interact with light at all, hence the name dark.
And dark energy, that's an even more recent and, frankly, more baffling discovery, right?
Precisely. Dark energy was discovered much more recently in the late 1990s, and it's even more enigmatic. It's some kind of mysterious force or property of spacetime itself that's causing the expansion of the universe to accelerate.
Speeding up, not slowing down.
Exactly. Mathematically, it's often represented by that cosmological constant lambda back in the Einstein field equations, but we don't really know what it is. So the central question becomes, are our theories of gravity, like general relativity, incomplete? Or are there entirely new types of particles and fields out there that we just haven't discovered yet? These mysteries are pushing the boundaries of both particle physics and cosmology. And while there are some alternative ideas, like modified Newtonian dynamics, MOND, or modified versions of GR, None have really managed to fully explain all the observations without invoking dark matter or dark energy yet. They represent a really profound challenge to our current picture.
Okay, so with all these huge unanswered questions and these competing theoretical frameworks, what's actually on the horizon for testing these ideas? How do we crack these cosmic codes?
Well, the good news is that technology is catching up to theory in some really exciting ways. A major upcoming experiment you should know about is the LISA mission, the Laser Interferometer Space Antenna.
Space-based gravitational waves.
Exactly. Unlike the ground-based detectors like LIGO, LISA will be a constellation of spacecraft in orbit, forming a huge interferometer. It'll be sensitive to gravitational waves in a different, much lower frequency range. This should allow us to detect things like the mergers of supermassive black holes in distant galaxies, and maybe even gravitational waves from processes way back in the very early universe. It promises unprecedented precision.
And what about getting a closer look at gravity's extremes? Peering right into the abyss, so to speak.
Right, that's where the Event Horizon Telescope, or EHT, comes in. This isn't a single telescope, but a global network of radio telescopes all working together. It's already given us that incredible first direct image of a black hole shadow, M87. And future upgrades promise even sharper images and more detailed observations.
So we can actually test general relativity right at the edge of a black hole.
That's the goal, to test GR in these extreme conditions. And beyond these big projects, there are other cool advancements too. Things like quantum sensors being developed for ultra-precise measurements of space-time curvature and enhanced space missions designed to test gravity with incredible accuracy, maybe even closer to home. All these technological leaps are absolutely key to finding the empirical evidence we desperately need.
So finally, let's zoom out. If we truly unlock the secrets of gravity, if we finally achieve this grand unified theory, what does that actually mean for us, for our understanding of reality, maybe even philosophy?
Well, if we connect this to the bigger picture, this whole journey of understanding gravity, it isn't just a scientific pursuit, is it? It's a fundamental human quest that constantly reshapes our worldview, pushes the boundaries of thought itself. I mean, just imagine if experiments confirm that space-time is quantized, that it's made of discrete bits. That could fundamentally redefine our basic concepts of space-time, cause and effect. Our everyday classical understanding of a smooth, continuous reality might just be an emergent property, something that arises from a deeper, stranger, discrete quantum reality. The philosophical implications of a truly complete theory of gravity could be immense. It could literally change our perception of reality, prompting entirely new questions about the nature of existence and, well, our place within it all.
Wow. What an incredible journey we've covered today. From Aristotle's ideas of natural places all the way through Newton's universal laws, Einstein's revolutionary warp space-time, and into the deep quantum mysteries of black holes, Hawking radiation, dark matter, dark energy. And looking ahead to the future observatories like LISA and the EHT that might give us answers. It's truly exciting to think about the ongoing research in gravitation theory. Our deep dive today was based on the really insightful work by Jürgen Schneppe in his essay Gravitation Theory, Understanding the Foundations of Gravity. If you're as fascinated as we are by these fundamental questions, and how could you not be, you can learn more about Jürgen Schneppe's work and related topics over at schneppet.de. That's SCHNEPPET.de.
So what stands out to you from today's deep dive? What new questions does all this ignite in your mind?
Yeah, it really leaves us with an important question for you, the listener, to ponder, doesn't it? If space-time itself really is quantum, if the very fabric of reality is woven from these discrete threads, what completely new kinds of reality might we uncover beyond our current understanding? And maybe more profoundly, what would that mean for how we perceive our own existence within it?
A huge question to think about. Thank you so much for joining us on this incredible quantum deep dive. Until next time, keep exploring.